Okay, so in this video, we are going to state and prove a general theorem which picks up on the observation we made in the previous video's examples, which was that the linear transformation T is 1-to-1 if when we find the standard matrix representation for that linear transformation A, and we write A in its equivalent reduced row echelon form, that A has a pivot in every single one of its columns. So let's state this more generally and prove this result. And so keep in mind that this statement that I wrote above in blue is equivalent to saying that the matrix A, that the homogeneous matrix equation AX equals 0 has only the trivial solution. So this statement up top and saying that this has only a trivial solution are equivalent. So we're going to state this theorem in using the matrix equation. And rather than write out the matrix, we're going to write this out using the transformation notation T. So what we're claiming here is that a linear transformation T is 1-to-1 if and only if the homogeneous equation T of x is equal to 0 has only the trivial solution. So the only vector in the domain which is being mapped to the 0 vector in the codomain is the 0 vector. So let's take a look at how this proof would work. And again, I realize not everybody in the course has had a class in proof writing, which would be Math 3000 at CU Denver, but it can't hurt to go through this, and certainly for the people that have taken Math 3000, it's really nice to see these proofs in practice. So here we have an if and only if statement. So that means if I want to prove this theorem, there are two things that I need to prove. I need to show that, first of all, what we'll call a forward direction, which is if this linear transformation is 1-to-1, then I want to prove that T of x equals 0 has only the trivial solution. And the implication goes the other way. So what we call the reverse direction of this proof would say, well, let's assume that T of x equals 0 has only the trivial solution. Then we need to show that that linear transformation is 1-to-1. So this is a double implication. So the forward direction will prove using a proof technique called proof by contradiction. And if you're not familiar with this proof technique or other proof techniques, that's okay. We'll illustrate what this proof technique is in this example. So how a proof by contradiction would start is we're going to assume the opposite of what we're trying to prove. So we're trying to prove that, okay, if T is 1-to-1, then this thing only has a trivial solution. So let's assume the opposite. Let's assume that T is a 1-to-1 function, but this equation Tx equals 0, that this has a non-trivial solution. So in particular, this vector v is not equal to the 0 vector. Well, we just reached a contradiction really quickly because we know that for one thing, for any linear transformation, the 0 vector needs to get mapped to the 0 vector. So now I have two different vectors, this vector v that we assumed is a non-trivial solution, and the 0 vector, they both get mapped to the 0 vector in the codomain. So we have just contradicted one of our assumptions, right? We assumed that T was 1-to-1. So what we've just shown is that it's impossible for a 1-to-1 map to have a non-trivial solution. So we've reached a contradiction, and that completes at least a forward direction. So now we're convinced that if T is 1-to-1, that the equation Tx equals 0 can only have just the trivial solution. So this direction was a little bit easier. Now we also need to prove the implication in the other direction, which is now we're going to assume that Tx equals 0 has only the trivial solution, and we'll see why that is going to imply that this linear transformation has to be 1-to-1. So we'll call this the reverse direction, and we're going to prove this using the same proof technique, proof by contradiction. So this proof by contradiction is going to start by, let's suppose that Tx equals 0 has only the trivial solution, and T is not 1-to-1. So let's see what happens under these two assumptions. Now we've assumed two things: that this equation Tx equals 0 has only the trivial solution, and we've also assumed that this transformation T is not one-to-one. So by assuming T is not one-to-one, this means there has to exist one pair of vectors, we'll call them u and v, right, where u and v are not equal to each other. So we have two different vectors in the domain which get mapped to the same image in the codomain. So we're going to assume that when I apply transformation T to u and I apply transformation T to some other vector v, these two vectors both have the same image, which is, we'll call this vector b, in the codomain. And let's see how this is going to lead us to another contradiction. So if that is the case, we can now use some properties about linear transformations. So namely, if I take the transformation T and I apply that to the vector u minus v, since we've assumed that u is not equal to v, then we know that this vector inside here is not equal to the 0 vector. And by properties of linear transformations, we can break up this difference into T of u minus T of v. And we assumed that we have two different vectors, u and v, that have the same image in the codomain. So both of these transformations that apply to u and v both get mapped to the vector b, and b minus b gives us the 0 vector. So now we have just shown that this map T has a non-trivial, T of x equals 0 has a non-trivial solution, namely the vector u minus v is a solution to the equation T of x equals 0. So that's a contradiction, since we assumed that this has only the trivial solution. We reached the contradiction, so this tells us that it would be impossible for both of these statements, that Tx equals 0 has only the trivial solution, and T not being one-to-one, to both be true. So therefore, if T of x equals 0 has only the trivial solution, this means that T has to be one-to-one. And that completes our proof. We've proven both the forward and the reverse direction using proof by contradiction. So here's a nice way of combining some of the concepts you may have seen in Math 3000 to some of the concepts we're now seeing in linear algebra. And on the very last slide, I just want to summarize this nice discussion about these properties of linear transformations, one-to-one and onto, and how they connect to the matrix representation for the map.